If you are building autonomous drones, mobile robots, or edge AI systems, you are constantly fighting a war against power. You need real-time perception, high accuracy, and low latency, but your battery doesn't care about your requirements. Conventional artificial neural networks are powerful, but they are hungry. They require massive compute and memory, often forcing you to offload processing to the cloud, which introduces latency and breaks autonomy. This is where neuromorphic computing enters the chat. Spiking neural networks, or SNNs, promise to process visual data with the efficiency of the brain, firing only when necessary. But theory is one thing, deployment on real hardware is another. In this video, we're breaking down a comprehensive benchmark study on real-time frame and event-based object detection, using spiking neural networks deployed on Intel's Loihi 2 neuromorphic processor. We're going to look at the architectural constraints of the chip, the engineering tricks required to squeeze detection models onto it, the use of knowledge distillation to close the accuracy gap, and how it stacks up against edge GPUs like the Jetson Orin Nano and Apple M2. This is a deep dive into the design, deployment, and benchmarking of SNNs on edge neuromorphic hardware. Let's get into it. First, we need to understand the hardware we're dealing with. Intel Loihi 2 is a research-grade neuromorphic processor featuring over 1 million hardware-fabricated neurons. Unlike GPUs that execute matrix multiplications on dense tensors, Loihi 2 processes information asynchronously using sparse, event-driven spikes. It natively supports leaky integrate and fire, or LIF, neurons. However, Loihi 2 comes with rigid constraints that force us to rethink standard CNN design. The chip requires pre-allocated activation neurons based on the model architecture and input resolution. This means you cannot dynamically resize inputs without recompiling the model. Furthermore, Loihi 2 currently lacks support for branching in convolutional neural networks. You cannot split feature maps into multiple parallel heads. It also only supports mean-only batch normalization, not the standard mean and variance approach used in most deep learning frameworks. These constraints dictate the methodology. The researchers developed 3 lightweight SNN architectures, all designed to fit within the 1 million neuron limit of a single Loihi 2 chip. To handle spatial resolution reduction without using max spooling, which is not spiking compatible, they replaced pooling layers with strided convolutions. They also utilized RepVGG-style blocks. RepVGG allows residual connections to be reparameterized into equivalent feed-forward connections at inference time. This is crucial for Loihi 2 because it eliminates branching, simplifying the execution graph. The detection head is another area of adaptation. Standard anchor-free detectors like YOLO 8 often use a decoupled head with separate branches for classification and bounding box regression. Due to the no-branching constraint, the researchers implemented a coupled head. Classification and regression are jointly predicted within a single unified head. A clever technical detail here involves the output layer. In SNNs, neurons spike when their membrane potential exceeds a threshold. For classification, this is fine. But for bounding box regression, we need continuous values. The researchers assigned a very high voltage threshold of 2048 to the output layer LIF neurons. This prevents them from spiking during inference. Instead, their membrane potentials accumulate over time steps, allowing the final potential to be interpreted directly as an analog output for regression. This is essential for accurate localization. Now let's talk training. Converting ANNs to SNNs often requires hundreds of time steps to converge, which kills inference latency. To maintain real-time performance, the team used direct SNN training with backpropagation through time, or BPTT. This allows the models to operate with far fewer time steps. They also employed 8-bit quantization-aware training, or QAT, to ensure the models could run efficiently on the hardware. However, directly trained SNNs often lag behind their ANN counterparts in accuracy. To address this, the study introduced an ANN to SNN knowledge distillation framework. This isn't just mimicking the final output. The distillation happens at 3 levels. First, feature-level distillation aligns the SNN's intermediate feature maps with the teacher ANN, using learnable 1x1 convolutions to bridge the representation gap. Second, classification-level distillation uses KL divergence on the output logits. Third, regression-level distillation aligns the distribution focal loss outputs for bounding box coordinates. This multi-level distillation allows the SNNs to recover between 87 and 100% of the detection accuracy of the ANN baselines, while maintaining low latency. The models were evaluated on both frame-based and event-based data. For event-based inputs, which come from dynamic vision sensors, they use 2 encoding methods, 2D 2-channel event histograms and voxel grid representations. Voxel grids preserve temporal dynamics by distributing events across temporal bins using linear interpolation, which proved beneficial for Model 3, which was initialized using weights from an event-to-image reconstruction framework. The benchmarking covered a diverse set of datasets. Regular objects were tested on Prophecy Gen 1 and Pascal VOC. Irregular anomalies, like cracks and spalling in civil infrastructure, were tested on the EV-Civil dataset. Additionally, the researchers introduced a new UAV-based tunnel inspection dataset collected from an abandoned tunnel in Spain, featuring concrete loss and water leakage defects, to test generalization on real-world field data. So what are the results? In terms of detection accuracy, directly trained SNNs without distillation showed an 11 to 27% drop in MAP compared to ANNs. But with distillation-aware training, the SNNs recovered the vast majority of that performance. On the tunnel dataset, the distilled SNN retained 94% of the ANN's detection accuracy. When it comes to performance metrics, Loihi 2 delivers real-time inference. The SNNs achieved inference rates ranging from 62 to 170 samples per second. This is significantly faster than the Jetson Nano B01, which struggled to keep up. However, the Jetson Orin Nano did achieve higher inference rates, running 1.34 to 2.6 times faster than Loihi 2. The real story, though, is energy efficiency. Loihi 2 is the clear winner for power consumption. SNNs on Loihi 2 achieved the lowest per inference dynamic energy across all platforms. Compared to the Jetson Nano B01, Loihi 2 was 10 to 35 times more energy efficient. Even against the more powerful Jetson Orin Nano, Loihi 2 consumed significantly less dynamic energy, despite the Orin being faster. In total power consumption, Loihi 2 outperformed the Orin Nano by at least 2.5 times, and the Apple M2 CPU by a wide margin. It is worth noting a nuance in the power profiling. On the Loihi 2 development board, static power dominates dynamic power. The static power consumption was found to be 2.5 to 5.2 times higher than the dynamic power incurred by the model execution. This suggests that for battery-powered edge devices, the baseline power of the neuromorphic board itself is a significant factor, and system-level optimization is critical. The study also analyzed the relationship between synaptic operations, or SOPs, and performance. SOPs measure the number of spike-based computations. As expected, higher SOPs correlated with higher dynamic energy and lower inference rates. The results reinforced that reducing SOPs through sparsity improves efficiency. Interestingly, they found that sparsity isn't just about the number of spikes. The activation of convolutional synapses matters too. In event-based data, fewer synapses were active compared to frame-based data, contributing to better throughput even when SOP counts were similar. Finally, let's discuss the limitations and future outlook. The accuracy gap between SNNs and state-of-the-art ANNs like YOLO 8N remains a challenge. A major contributor is the mean-only batch normalization constraint on Loihi 2. Next-generation neuromorphic hardware is expected to support standard batch normalization, which should close this gap. Additionally, the lack of support for complex architectures like convel SDMs and multi-scale branching limits the model capacity. As neuromorphic chips scale, such as Intel's upcoming Hollow Point system, we should see the deployment of larger, deeper SNNs. Event-based vision offers clear advantages in high dynamic range and low latency, handling low light and overexposed scenes better than frame-based cameras. However, DVS sensors lack color and static information, which can lead to ambiguity. A hybrid sensing approach that fuses event data with frame-based imagery is likely the path forward for robust inspection tasks. In conclusion, this work demonstrates that neuromorphic systems can perform real-time object detection with exceptional energy efficiency. By adhering to hardware constraints, using rep parameterization, coupled heads, and distillation-aware direct training, SNNs on Loihi 2 can recover most of the accuracy of ANNs while maintaining real-time rates and minimizing energy consumption. While accuracy still trails behind high-end edge GPUs, the energy delay product and power efficiency make neuromorphic computing a compelling solution for battery-constrained autonomous systems. As the hardware matures and supports more complex architectures, SNNs are poised to become a standard tool in the edge AI engineer's toolkit. If you found this deep dive into SNN deployment and neuromorphic benchmarking useful, check out the linked resources in the description for the full paper, code, and dataset. Thanks for watching, and keep pushing the boundaries of efficient AI.